Hi, it's Sir Eldon Calamba and welcome to Physics for Engineers. Let's go! This is examples for motion in one dimension. I hope you have studied the lecture note and you have read chapter 2 and reviewed the video lectures. Now we will have the sample problems. The sample problems are also uploaded in our data. So let's have example number 1. So example number 1, the position versus time graph or the position versus time or position time graph for a certain particle moving along the x-axis is shown in the figure. Find the average velocity in the following time intervals: 0 to 2 seconds, 2 to 4, 4 to 5 seconds, 5 seconds to 7 seconds, and 7 seconds to 8 seconds. So you are given there a position versus time graph or position time, wherein by inspection your position is in the meters and your time is in seconds. You are ought to find the average velocity. The average velocity that is just coming from the slope, wherein the is rise over run, or this one, the change in x over the change in t, or that is the change in position with respect to the change in time. So if you're finding an average velocity or an average value, always remember that you're given 2 points, the initial and then the final point. So this time we are given the initial and then the final point for our time. So you have initial and final time, wherein the final time is 2 seconds and the initial time is 0 seconds. So from 0 to 2 seconds. So we have to find the average velocity. We have to find the slope. So for letter A, that is just delta x over delta t. So that is, this will become your x2 and this point at 0 second will become your x1. So you have x2 minus x1. So that's 10 meters minus 0 over 2 seconds minus 0 seconds. So your average velocity for this one along the x-axis is positive 2 meters per second. Again, positive 2 meters per second. And take note that slopes will always give you a positive or negative value. And as you can see, by inspection also, from that time interval, we should get a positive slope or a positive average velocity. Letter B. For the average velocity for the time interval 2 seconds to 4 seconds. So from 2 seconds to 4 seconds. So what is the slope here? As you can see, it is diagonally down, pointing downwards. So we expect a negative value. Okay, so this will become your x2 and this will become your x1 with corresponding t2 and t1. Okay, so the average velocity along the x-axis for that one, that is 5 meters. As you can see, this is our x2. This is in between our 4 meters and 6 meters. So this is 5 meters. So 5 meters minus 10 meters over 4 seconds minus 2 seconds. T2 minus T1. So we have an average velocity of negative 2 meters per second. So that is now our answer. For letter C, 4 seconds to 5 seconds. 4 seconds to 5 seconds, this is coming from this point going to this point. As you can see, we only have a horizontal line. Obviously, there should be no slope there, or the slope should be equal to 0. So it's up to you if you want to solve it mano-mano, if you really want to show it. But I understand also that you will just input there 0. Okay, so that is just from 5 meters minus 5 meters over 5 seconds minus 4 seconds. 5 minus 5, it is 0. So you have an average velocity of 0. So that's for your letter C. For letter D, you are ought to find the average velocity from 5 seconds to 7 seconds. So from 5 seconds from this point to 7 seconds. So you now have this one will become your x1, that is 5 meters. And then this will become your x2, wherein in between -4 and -6, so -5. So you have an average velocity of -5 meters minus 5 meters over 7 seconds minus 5 seconds. So the average velocity is -5 meters per second. And lastly, you have letters E, the average velocity from 7 seconds to 8 seconds. 7 seconds to 8 seconds. By inspection again, it should be positive. So it is coming from -5 x1 and then x2 is 0. So x2 minus x1 is 0 minus -5 over 8 seconds minus 7 seconds. So we have an average velocity of positive 5 meters per second. Okay? So that's for our example number 1. This example number 1, we could extend the question. Okay, so let's have this example number 2. Same graph. The position versus time graph for a certain particle moving along the x-axis is shown in the figure. Again, this figure again. Okay, find the velocity in the following time. So velocity, and then number 1 is average velocity. When we say velocity, it should be understandable that we are pertaining to instantaneous values. Hence, the given time for our example number 2 is only at 1 point. It's very specific. So you have 1.5 seconds, 2.5 seconds, 4.5, 6 seconds, and 7.5 seconds. Okay, so if you're going to trace that one here in our graph, so you have here 1.5 somewhere here, and then you have the 2.5 seconds in between, and then you also have 4.5, 6 seconds, and 7.5 seconds. Now, I understand that if you are to get that one, the instantaneous velocity or velocity, it will be difficult for you to analyze that one. But this graph is particularly or relatively easy compared if you have a parabolic curve or parabolic na graph. Why? Because these are just straight lines. Okay? Straight lines, meaning to say, the slope at any point, let's say for example, from 0 to 2 seconds, the slope at that time interval will just be the same. Whether you are at 0 second, 0.5 seconds, 1.5, or 1.8, the slope will always be the same. Okay? So I've written it here. If slope is constant for a position versus time graph, just like what you can see from 0 seconds to 2 seconds. In given time interval, the average velocity and velocity, instantaneous velocity of that time interval is the same or constant. So meaning to say, the average velocity should be equal to its instantaneous velocity. So it's kind of no-brainer now to answer this example number 2. It is fairly easy if you have computed for the slope already. If not, then you have to pinpoints or 2 points again, to pinpoint 2 points again, the final and then the initial, wherein your line will coincide so that you could get the slope. Just remember that average velocity is just the slope of a tangent, of a secant line, while your instantaneous velocity is the slope of a tangent line touching at 1 point. Okay? So for this, it's kind of easy. So we could easily answer this example number 2. So the velocity at 1.5 seconds should be equal to the slope from 0 to 2 seconds. We have positive 2 meters per second. The velocity at 2.5 seconds, so it should be equal to the slope of the time interval 2 to 4 seconds. So you have negative 2 meters per second. And obviously, at 4.5 seconds, we have 0. And then letter D, 6 seconds, we have negative 5 meters per second. And lastly, for 7.5 seconds, it should be positive 5 meters per second. Okay? So that's for number 2. It's kind of easy to solve number 2 if you have understood or you have solved number 1. And this problem again can be extended to another question. So given the position versus time graph of a certain particle moving along the x-axis as shown in the figure, draw the velocity time graph of the given position time graph. So you have to translate this position time graph going now to a velocity versus time graph. So what will happen is that for you to answer this one is that you have your vertical axis now in terms of velocity and your horizontal axis in terms of time. So your vertical axis is in meters per second and your horizontal axis should be in seconds. It is up to you how you will denote the intervals, but I have this answer now, or this graph. So you have the vertical meters per second. I have the time now. I have the time in seconds. Okay, now as we have learned from number 2 and number 1 is that the slope will just be equal from 0 to 2 seconds. Hence, the speed or the velocity should be the same. That's why I have the answer here, or the line now, or the horizontal line, that is 2 or positive 2 meters per second. As you can see, the slope is constant. Okay, we just have to graph the slope now. The slope that we got from number 1 and number 2. So as you can see, from 0 to 2 seconds, it should be constant at positive 2 meters per second. Next is, we have the time interval 2 to 4 seconds. So from 2 to 4 seconds, we have negative 2 meters per second. We have here straight line again. Next, from 4 to 5 seconds, the time interval, we have 0. So we have the horizontal line at 0. And then from 5 seconds to 7 seconds, we have negative 5 meters per second. And lastly, from 7 to 8, we have positive 5 meters per second. Okay, so as you can see, we don't have diagonals anymore. We don't have a slope because our position versus time graph shows a constant slope at given time intervals. But be mindful that you don't have to connect from positive 2 meters per second going to negative 2 meters per second because we don't have any idea what happened there. So I just used a broken line. Okay, now this velocity versus time graph will give us again two data. We could get the slope, which is the acceleration or average acceleration, or you could get the area under the curve. The area under the curve will give us displacement. So that's for your example 1 to example number 3. Let's go now to another example number 4. So a lunar lander is descending, going down towards the moon's surface. Until the lander reaches the surface, its height above the surface of the moon is given by position as a function of time. This is in terms of y. That is equal to b minus ct plus dt squared, where b is equal to 800 meters. Is the initial height of the lander above the surface, so positive 800. We have c that is equal to 60 meters per second, and d 1.05 meters per second squared. Calculate for a, the initial position of the lander, the initial velocity of the lander, and initial acceleration of the lander. Okay, now take note, we are just after the initial value. So at t equal to 0. So just remember, if you are after initial values, it's always calculated at 0 seconds. Okay, so what we are given is a position as a function of time. So you have yt that is equal to b minus ct plus dt squared. Or if you want to substitute already you may do so. So you have y of t that is equal to 800 meters minus 60 meters per second t plus 1.05 meters per second squared t squared. So initial positions, initial position, initial velocity, initial acceleration. So initial time at t is equal to 0. What is the position? All we have to do is that if you have a position as a function of time, then you just have to substitute a value of time and then you could get the position. So that's the first step. So the first solution, you just have to substitute 0 seconds to all of these variables t. So we have now the initial position that is equal to 800 meters. Positive 800 meters. Letter B, find the initial velocity of the lander. So velocity, that's an instantaneous value. So what we're going to do is that from a position from a position as a function of time, we have to derive it once in order for us to have a velocity as a function of time. So we have to find the first derivative. So we have to derive this one or this one if you want. So I don't want to have any lessons again about derivatives because you have that one in senior high school and you also had that one last time. So the position now as a function of time, we have this one. Position as a function of time equation. Vy of t, again Vy, it becomes Vy. From position as a function of time going to a velocity as a function of time. We have negative 60 meters per second plus 2.1 meters per second squared t. Okay, so what we're going to do is that we just again we have to substitute the time or the initial time 0 second. Okay, so we substitute 0 second to our variable na t. So y of t now, or Vy again of 0 seconds at 0 seconds is equal to negative 60 meters per second. So as you can see, you have as negative 60 meters per second value, you have a negative value. That is because the motion of our lander or lunar lander is that it is going down. So velocity is going down, pointing downward. So you have negative 60 meters per second. Next, we have to calculate for the initial acceleration of the lander. So if we talk about acceleration, we have to derive it again. If coming from velocity as a function of time, you just have to derive once. But if you're coming from a position as a function, as a function of time, you have to derive twice. So if you're given this, just like this one, y as a function of time, so you have to get the second derivative. So me, I'll just make use of my velocity as a function of time. I will make use of this one. So I have to derive this equation. So my acceleration now, upon deriving this, we now have this one, wherein ayt is equal to equal to positive 2.1 meters per second squared. So as you can see, there's no variable time t anymore. We cannot substitute anything there. But we have to understand is that if there's no more variable t for you to substitute, most probably because it is under constant acceleration. Meaning, at any time t, it should have an acceleration of 2.1 meters per second. We now go to example number 5. Okay, so a car travels in a positive x direction on a straight line and level road. For the first 4 seconds of its motion, the average velocity of the car is 6.25 meters per second. How far does the car travel in 4 seconds? So we all know that the change in time t2 minus t1 is 4 seconds. The average velocity is 6.25 meters per second. Let's assume that our car is not assume pala. It is stated there, it is moving in the positive x direction. So you have the change in position x that is in positive. So wherein the magnitude of delta x, that is just our distance. But our direction is going positive. Most probably we have a positive value here. For all we know that our average velocity is just equal to the change in position over the change in time. So delta x is just equal to average VF average velocity times delta t. So we could easily substitute. So 6.25 meters per second times 4 seconds. We now have delta x that is equal now to 25 meters. Positive 25 meters. So that's for example number 5. Example number 5, it's fairly easy. We now have to answer the preceding examples in terms of this one. We're done with the graphs. So let's have example. Let's have example number 6. Okay, so a rocket starts from rest and moves upward from the surface of the Earth. So moving in the above the Earth. For the first 10 seconds of its motion, the vertical acceleration of the rocket is given as 2.80 meters per second cubed p. So you can see you have an acceleration as a function of time, where the positive y direction is going up. A. What is the height of the rocket above the surface of the Earth at t is equal to 10 seconds? So we have to get a position, the distance. B. What is the speed of the rocket when it is 325 meters above the surface of the Earth? Okay, so you have here your position, acceleration as a function of time. Let's assume at t1 we have the initial time at 0 seconds, nasa Earth pa siya, and then starting from rest, v1y that is equal to 0. For all we know, y minus yo is just equal to delta y, and then we have to find this change in position because this is our height actually that we have to get. At t is equal to 10 seconds, where is our rocket? If our yo is just equal to 3 or we could have it as a delta y na lang, because the delta y is just equal to the height where the rocket should be after 10 seconds. So this is from our last topic from our video lecture, wherein we will be using integration. So we have here vy equal to v1y plus ay dt, or the integral of ay dt evaluated from 0 seconds to time t. I will just take note this as time t pala, the upper limit. Okay, so we know that v1y, this is just equal to 0 because it started from rest. So we could have vy lang that is equal to this quantity. We have to substitute this ay here going to this ay. So we have now the integral of 2.80 meters per second cube t dt evaluated from 0 to t. For all we know, 2.80 meters per second cube is a constant. We could take that one out. Okay, so we now have 2.80 meters per second cube times the integral of t dt evaluated from 0 to t. If integral is just the opposite of derivatives, we know that this t here, if we have to go back, if we want to go back to its original form, this is just it should have a power of 2. Hence, we have to multiply our integral with 1/2. So we have here this over 2 here. Okay, so we can now easily derive this t. So we now have, because for all we know, there should be 2 here in order for us to bring the 2 sa exponent. And in order for this to equate, we have to multiply both sides by 2 over 2, wherein 1/2 pwede natin ilabas. And then we have 2 here natira. Okay, so we now have this equation wherein you have 2.80 meters per second cube over 2 times t squared. Don't forget, t squared na yan, evaluated from 0 to t. This value sa 0 to t, we have to substitute that one here. So our t squared, wherein it is always from final minus initial, upper limit minus the lower limit. So this will become t minus 0 if you want. But let's simplify this one first. 2.80 divided by 2. So we now have this 1.40 meters per second cube. What happened to the t? So for all we know, the lower limit is just 0. We could neglect this. What would happen is that this is just equal to t squared minus 0 squared. So it will just be 0 squared, 0. So we now have this equation. So from an acceleration as a function of time, we now have a velocity as a function of time. And from the previous lecture, we have this equation wherein we have the change in position, or we have y equal to yo plus the integral of v2y, or the integral of vy dt, or the integral of v dt evaluated from 0 to t. We already know this should not be v2y. This could be vy. We already know the equation for vy. We got that one from the previous one. So we substitute this value going here. Okay, so we have here y minus yo. Take note, ito yung hinahanap natin kanina. The change in y, the height of our rocket after 10 seconds. So we now have, after substituting this one here kay vy, we now have the integral of 1.40 meters per second cube t squared dt evaluated from 0 to t. Okay, so 1.40, this is just a constant. Could take that one out, of the equation, of the integral sign. So we now have 1.40 meters per second cube, the integral of t squared dt evaluated from 0 to t. So this is t squared. Again, the opposite of derivative is integral. So in order for us to integrate this one, we have to multiply here with 3. So multiply that with 3, and then we have to we also have to divide our 1.40, or we have to multiply with 1 over 3, or 1/3. So 3 now will go up. So 2 plus 1 na yan siya kaagad, diba? So we now have 1.40 meters per second cube over 3 times t cube evaluated from 0 to t. So doing again what we did with this one. So we now have y minus yo, or delta y, that is equal to 0.4667 meters per second cube t cube. We now have the change in position of our rocket with as a function of time. So we just have to substitute our value of time here by t, and we know we are finding the height at t is equal to 10 seconds. So substitute 10 seconds here, we now have the answer, that is y minus yo, that is equal to 467 meters. Again, my answer is I'm evaluating the given. We have the least significant figures, we have the 3 significant figures lang. So my answer should be expressed in 3 significant figures. That's why I have 467 meters. Let's now solve for letter B. So what is the speed of the rocket when it is at 325 meters above the surface of the Earth? So we now have the change in position that is equal to 325 meters. So what we're going to do is that we're just going to solve for the time t. So this one, this equation, we have the y minus yo. We could easily substitute 325 meters there and get time t. Okay, so that's what we're going to do. So if vy, if y minus yo is 325, substitute 325 here to this equation. Okay, so we have t now that is equal to the cube root of 325 meters over 0.4667 meters per second cube. So we have now the time t that is equal to 8.863 seconds. And then get the time. So we have to get, not the time rather, we have to get the speed pala. So what is the speed? Sorry. So we have to solve for the speed. So we go back again to this equation. To this equation. Vy, that's equal to 1.40 meters per second cube t squared. Because we have already solved for time t. And that is 8.863 seconds. I'm sorry for the chickens. So we have Vy that's equal to 1.40 meters per second cube times 8.863 seconds squared. So the answer is Vy now is equal to 110 meters per second. So that's for example number 6. Let's have example number 7. An electron in a cathode ray tube accelerates from a speed of 2.00 or 2 times 10 raised to 4 meters per second to 6 times 10 raised to 6 meters per second over a distance of 1.50 cm. In what time interval does the electron travel this distance of 1.50 cm? What is its acceleration? And then assume that it is under constant acceleration. Please notice the change in speed from it is using scientific notation. You have there times 10 raised to 4 and then it becomes times 10 raised to 6. So scientific notation, it's you're using that one and then you analyze this, the change in velocity or the change in speed of our particle or of our electron is very very fast. From 2 times 10 raised to 4 it becomes 6 times 10 raised to 6. So we actually, for over a very very short distance, so we are actually expecting high values here. Okay, so this is under UAM. So it is understandable that we have to make use of our UAM equation. So you have here V2 equal to V1 plus AT, X2 minus X1 plus equal to 1 half V1 V2 T, and so on and so forth. So what I want you to do this with this one is that you have to compartmentalize yourself, wherein you have to write all the givens first and then you decide what equations to use. It does not mean that if you will be using one equation, you will not use the others. So you have to make sure also that if you're going to use this equation, let's say for example you have already used up three equations and you did not see any and you did not solve any of the problems or any of the variables yet, just make sure that these multiple equations can be simultaneously solved. We have discussed this one in our algebra, wherein you have, if you have three unknowns, it will require you three equations. If you have four unknowns, it will require you four equations, systems of linear equations. So it's very important for us to learn also algebra and not forget about algebra in answering UAM, because this is very particular with its equations. So we just have to play around with these four equations. Okay, so what do we have? We have V1, the initial velocity, 2 times 10 raised to 4 meters per second. And then we have the final velocity, 6 times 10 raised to 6 meters per second, sorry. And then we have the change in position, x2 minus x1. I just assumed that we are moving in the horizontal axis or positive x-axis. So you have there 1.50 cm, or that's 1.5 or 1.50 times 10 raised to negative 2 meters. So I also assumed that at V1x at this point, I have the time t1 0 second. Okay, so we are after first, in what time interval does the electron travel this 1.50 cm? So at what time daw nandito or ganito ang speed ni electron at 6 times 10 raised to 6 meters per second, or if it has traveled 1.50 cm, at what time will it reach 1.50 cm? So you inspect your four equations or what you will be using. For me, I'll be using this one, x2 minus x1 plus 1 half v1x plus v2x t. And then hinahanap is time, so I will just isolate time t. So t now is just equal to 2 times x2 minus x1 over v1x plus v2x. Then you substitute all your variables, x2 minus x1 or the change in position. You have here 1.50 times 10 raised to negative 2 meters over all over v1x plus v2x. I have here 2 times 10 raised to 4 meters per second plus 6 times 10 raised to 6 meters per second. So it will reach this speed or this distance at t is equal to 4.98 times 10 raised to 9 raised to negative 9 rather seconds, or that is 4.98 nanoseconds. See, that's a very very fast particle. It's moving at a very very fast rate. Okay, so letter B, what is its acceleration? So for the acceleration, you could make use of the time t, you could take advantage of this one, or you could just stick with the given. For me, it's always a rule of thumb for me that I have to look at again my equations. I will just stick first with a given, and if I will stick with a given, can I get another one? Can I get another unknown? Can I get the acceleration, or can I get another speed, or can I get the time again? Okay, and then if there's nothing left to do but to substitute the solved variables, let's say for example at this one for this one is time t, there's no way out, then I will make use of my solved variables. Okay, but for me, nakita ko, I could make use of this equation. That is v2x squared equal to v1x squared plus 2ax times x2 minus x1. I will not be using the time t, but if you want, you could make use of that one. I'll just stick with my rule of thumb na if kaya pa sa given, then I will make use of the given. So I'll have to calculate for the acceleration. So this is just equal to v2x squared minus v1x squared over 2 times x2 minus x1. Substituting all the given, and don't forget the squared. Okay? Some students really forget to do the squared thing or raise it to 2, then they'll have wrong answers. Even though the problem is very very easy. Okay, so we now have ax equal to 1.20 times 10 raised to 15 meters per second squared. Take note, times 10 raised to 15. Now that's a very fast acceleration. We now have example number 8. A truck covers 40 meters in 8.50 seconds while smoothly slowing down to a final speed of 2.80 meters per second. A. Find its original speed, and B. Find its acceleration. Let's assume that it is under constant acceleration or UAM, so that we could still make use of our equations, of our 4 equations. Okay, so let's have number 8. So we have the change in position that is just equal to 40 meters, wherein it took the change in position at just t is equal to 8.50 seconds, with its speed reaching 2.80 meters per second. Let's assume that it is moving in a positive x direction, so that I will have the velocity positive 2.80, and then the change or the change in position is just positive 40 meters. So any of the 4 UAM formulas, we can make use of that one. So finding the original speed. So we have the change in position, we have the time 8.50 seconds, and we also have the final velocity. Why not make use of this equation? X2 minus x1 equal to 1/2 v2x plus v1x times t. So we are just after the speed or the initial speed, the original speed. So we could isolate v1x. So we could solve v1x, which is just equal to 2 times x2 minus x1 over t minus v2x. Substituting all the known values, we could get the speed now that is equal to 6.61 meters per second. Okay, so yeah, we have the speed that is the magnitude of this velocity. It's just 6.61 meters per second. It's just the same. So let's have letter B, finding its acceleration. So huwag ka nang lumayo. We have already equation number 1. That's very easy. We know the initial, we know the final, and all of these equations, number 3 and number 4, is also taking or making use of the initial velocity, which is what we have solved in letter A. So wala tayong kawala. let's make use of the easiest or the simplest one, equation number 1. So we have v2x that is equal to v1x plus ax times t. So we now have ax that is equal to negative 0.448 meters per second squared. Why do we have a negative answer? As you can see what we have here in the problem, while smoothly slowing down. So if it is slowing down, and then we have assumed that we have positive velocities, then our acceleration should be negative. So that you have the velocity vector and your acceleration vector pointing towards the opposite direction, wherein it tells you that our object or our truck must be slowing down. Let's go now to example number 9. So, when startled, an armadillo will leap upward. Suppose it rises 0.544 meters in its first 20 seconds. A. What is its initial speed as it leaves the ground? B. What is its speed at the height of 0.544 meters? And C. How much higher does it go? Or what is the change in position from the 0.544 meters? Okay, so let's have this one. This armadillo is, or armadillo, I don't know, it's an armadillo. It is under free fall. Where in free fall, freely falling bodies, it is under constant acceleration. And our acceleration this time is just equal to negative of g, negative 9.8 meters per second squared. And as you have noticed, I just replace all the x's with y's. Okay? So, I assume that the armadillo is coming from the ground, wherein that is my yo. And that is equal to 0 meters. So this one, at the ground. At t is equal to 0 seconds. And then, after leaping, it reaches a height of 0.544 meters. That is y1. At t1 is equal to 0.200 seconds. So, the first problem is we have to solve for the speed as it leaves the ground. So, I assume that my motion going upwards as positive. So, it's coming from the ground, so it's positive all throughout. So, my speed or my velocity should be pointing upward. So, what is the velocity or the magnitude of this velocity will be the speed of VOY. So, upon inspection, I could easily make use of this equation. This is our equation number 2. Y1 minus YO. I have analyzed the problem from point 1 going to from point 0 going to point 1. Okay? So, I have delta Y that is just equal to 0.544 meters. So, evaluating and substituting all the values from that equation, I could solve for my initial speed. That is 3.70 meters per second. So, these are just the algebra part. Okay, the answer is 3.70 meters per second. Next, the problem, letter B, what is its speed as it reaches the height 0.544 meters, or what is V1y? So, making use of equation 1, V1y equal to VOY plus AYT. So, we could easily solve for V1y by substituting the VOY and the time t that we got here from the problem. So, V1y is just equal to 3.31 meters per second. Okay? So, that's how we solve for letter B. At what is its speed at the height of 0.544 meters? Letter C. How much higher does it go? So, what's the additional height from the 0.544 meters? So, how much higher does it go is actually talking about the maximum height. Okay? So, because that's the maximum height that the armadillo will reach. Okay? And then at maximum height, Vy will always be equal to 0. So, we already know the initial speed, so why not make use of this one? Because upon inspection of the given, we could make use of this equation. So Vy squared equal to V of y squared plus 2ay times y max minus yo. I'm analyzing it from point 0 going to the maximum height. Hence, I have here yo, wherein yo from the ground is just equal to 0. This will just cancel out. So I have Vy squared that is just equal to 0 because of maximum height. The speed is 0. So 0 equal to V of y squared plus 2ay times y max. So I have to solve for y max. I now got 0.698 meters. That's the maximum height that will be reached by our armadillo. And then getting y, the additional height, there will be an additional height now that is coming from y max equal to y1 plus y. The additional height will be 0.154 meters. Again, it is the additional height. So I just subtracted the maximum height with the initial height that the armadillo will reach. That is 0.698 meters minus 0.544 meters. So my additional height will be 0.154 meters. Let's now go to number 10. It's kinda, I think 10 is kind of low. Yeah, it's kind of low, but it's very easy to answer this one. So a rock is shot vertically upward from the edge of the top of a tall building. The rock reaches its maximum height above the top of the building 1.60 seconds after being shot. And then after barely missing the edge of the building as it goes downward, the rock strikes the ground. Okay, the rock strikes the ground. It will not touch or it will not reach the initial position. It will reach the ground after 6 seconds. Okay, letter A. With what upward velocity is the rock shot? B. With what is the maximum height above the top of the building is reached by the rock? And C. How tall is the building? So for this one, it's better for me to illustrate. So we have here the building. This is the building. And then I have here the rock, color red. And then it will be vertically shot upward. So it will reach maximum height. And then it will pass by the ledge or the edge of the building and goes to the ground. So I have 3 points. Point 0, point y max, and then I have here point y2. For y max, it is measured from the height of from the top of the building. That is our y max. Okay? Because the question also letter B, it is with respect to the height of the building. Okay, so for this one, so 0.0, point y max, and point y2. And at point y max, I have there y1 also. So y max is just equal to y1. So I made the top of the building as my reference point. Hence, I have there yo that is equal to 0 meters. So anything that is measured going up in terms of position will be positive, and then anything else that is measured below that 0 meters in terms of position will be negative. Okay, so let's have letter A. With what upward velocity is the rock shot? So I will be analyzing this one from point 0 going to that maximum height, wherein at maximum height I have the speed that is just equal to 0. Okay, so I will make use of my equation number 1. This one. This one. Okay, so V1y is just equal to VOY plus AYT. And V1y, the final velocity or the final speed at y max is just equal to 0. So cancel out 0. 0 is equal to VOYT plus AYT. I know the time that it will reach the maximum height, that is 1.60 seconds. Substituting that one here kay time t. And then for all we know, AY for a free fall is always negative 9.8 meters per second squared. So we could easily get VOY or the initial upward velocity of the rock. So VOY is positive it is 15.7 meters per second. Okay, so we have here the velocity positive 15.7 meters per second. I always write the positive one. The positive or if it is negative. Next question. we are asked about the maximum height. So we will still be analyzing it from point y0 going to point y1 or y max. So hanap ka ngayon sa equation mo saan doon ang may y max. So ako, gusto kong gamitin na lang ito na equation. Ayoko yung may e squared kasi ayoko na mag squared pa. So I will make use of this one. Galing lang ito, saan ba ito? Let's check. Saan ba ito galing? Ayan. Galing lang ito sa second equation natin. Okay, so y max is just equal, y max now, solving for y max is y max minus yo is equal to 1/2 voy plus v1 yt. And then yo, this is just equal to 0 meters. And then v1y, that is just 0. So we could easily solve for y max. So y max, substituting all the known values, we have 12.6 meters. Positive 12.6 meters. That is the maximum height reached by our rock. Next is the last one. How tall is the building? So solving for the height of the building. So this y here. So I will just get the change in position in terms of yo going to y2. So y is just equal to delta y. So y is just equal to y2 minus yo, getting the magnitude, wherein we know, for all we know, yo is equal to 0. Hence, the height of the building is just equal to the absolute value of y2. Because ang masosolve natin na y2, it will be negative. Because it is y2 is pertaining to position, not distance. Okay, and then we made the top of the building as our reference point, and everything going down the position will be negative. So we have to get the absolute value. So y2 now, I will make use of this equation. This is the third equation. That is y2 minus yo. Again, I'm analyzing it from point 0, point O, going to point 2. So y2 minus yo equal to voyt plus 1/2 ay t squared. So yo 0. y2 now, substituting all the known values, I have this answer. y2 is just equal to negative 82.2 meters. Again, it is negative because it is pertaining to the position pa. It is not pertaining to the height of the building. So the height of the building y is just the absolute value of y2. Hence, y now is just equal to positive 82.2 meters. So that's for example number 10. Actually, this is the last example for motion in one dimension. So please take note of all the concepts that I have discussed here, and then go now to the lesson 2.2. Bye!